So far we have discussed what are complex valued functions and what are the mappings associated to them. So mapping is a geometrical way of visualizing a given complex valued function. And of course, it helps us in understanding the behavior of the function. From now on, we are going to choose some particular examples of complex valued function and discuss the mappings associated to them. Our first example is going to be linear transformations. Now these are some very simple but important elementary complex valued functions, and they have some very interesting geometrical interpretations as well. Now this is the first part of our discussion on linear transformation. Now let's recall what is a linear transformation. It is a linear polynomial, so it's a particular case of a polynomial where we have the form L of z is equal to az plus b. Now a and b are fixed complex numbers and z is the complex variable. Now if we change the values of a and b, then we will be getting some particular examples of linear transformation. Now from further on, we are going to choose some particular cases where we choose some particular values of a and b and see their geometrical interpretation, or we see what are the mappings associated to them. Our first example is the case of translation. So in this translation, we choose a to be equal to 1 and b is any complex number a plus iota b. Now in this case, we call it t. So t stands for the translation. So t of z becomes z plus b. In particular, if z is equal to x plus iota y, then t of z becomes x plus iota y plus a plus iota b. Now if we collect the real and imaginary parts, the expression becomes the following: y plus b. Now this is the real and imaginary parts of this complex valued function. Now let's see what is the geometrical interpretation of this function. Now as we can see that when we apply t on a complex variable z, then we add this complex number b, which is a fixed complex number. Every time we apply this t on z, we add this complex number b. So if we represent this complex number b by a vector in the complex plane, then basically when we are applying t on z, then we are translating this z through this vector b. So in particular, if we have a set A, which is the rhombus in this complex plane, then applying t on this A means that we are displacing this rhombus in the complex plane through this vector b. Okay, so why this is the case? Because each number of this rhombus is translated by this vector b. So in particular, so this part of the rhombus goes to this vertex. This part of the rhombus goes to this vertex, and this part of the rhombus goes to this vertex, and up to so on. And in particular, if we have any point inside this rhombus, then this is also translated through this vector b. So each and every point of this rhombus is translated by this vector b. So in other words, the whole rhombus is translated. And of course, if we change this vector b, then of course the translation, the direction and the magnitude of the translation will also be changed. Okay, so we can see that when we are changing this vector b, then the translation, the direction and the magnitude of this translation is also changed. Okay. So in this picture, we can see the images from the z plane and images from the w plane in the same complex plane. This helps us in understanding the behavior of the function more efficiently. Now the next observation is these translations are one-to-one and on-to function on the entire complex plane. So in other words, we can talk about what are the inverses of these linear transformations, these particular case of linear transformation. So in this case, if we assume that w is equal to t of z, w is the output and Z is the input. So in this case, this is equal to Z plus B. Now we know that if the function is 1 to 1 and on to, then we can solve the function in terms of W. So which is very simple in this case. We can find the value of Z in terms of B. So this becomes W minus B. So this implies that the inverse function is basically W minus B. Okay, and if we use the same variable, so this implies that F inverse of Z is equal to Z minus B. So this is the inverse of this translation. And we can see that in this case, we are subtracting this vector B. So in other words, this is kind of inverse translation. So if we apply this translation, then we move through this vector B. And when we apply the inverse translation, we are moving back with a vector minus B. So that's why they are inverses of each other. Okay, so in particular, if we calculate T inverse of W, and if we take the components of W to be U plus iota V, then the form of the inverse translation becomes U minus A, this is the real part, plus iota V minus B, this is the imaginary part. Now the next particular case of linear transformation is rotation. Now in the case of rotation, we take B to be equal to 0 and we choose this complex number A such that its modulus is equal to 1. So let's see what will happen in this case. So the linear transformation becomes R of Z is equal to A into Z. Now if we want to understand its geometrical meaning more efficiently, then we use in this case polar coordinates. So if the modulus of A is equal to 1, so the form of A becomes e raised to power iota alpha, where alpha is the argument. And if we choose Z to be equal to R e raised to power iota theta, then in this case the rotation function becomes R of Z is equal to R e raised to power iota alpha e raised to power iota theta. So which is equal to R e raised to power iota alpha plus theta. So this is the rotation linear transformation. Now why this is the rotation? Now we can observe that when we apply R on this complex number Z, then the output is R e raised to power iota theta plus alpha. Now the input is Z is equal to R e raised to power iota theta. So what is the difference between input and output? Now the modulus of Z is not changed. So what is changed is basically this argument. So the argument is increased by this angle alpha. So in other words, if we take a complex number and if we apply this transformation R on Z, then the number will be rotated around the origin because the angle of this, the argument of this complex number has been increased. Okay, so if this is our complex number, then it will be rotated by an angle alpha. Okay, so it becomes this. So let's say if this is Z1, then this is R of Z1. Similarly, if we have another number, let's say Z2, then it will also be rotated by an angle alpha, R of Z2. And similarly, if we have origin, then the origin will remain the same. So in particular, if we choose a set A, which is a triangle, then applying this rotation transformation on A means the whole triangle is basically rotated around the origin. So now we can see that if we change the value of alpha, then the rotation will be changed. So as we increase alpha, the whole square is translated. And of course, if we choose some other subset of the plane, then it will also be rotated. Now the important thing to observe is this transformation is rigid. So why this transformation is rigid? Because the shape of this set is not changed. Okay, so square remains the square and this arbitrary shape remains the same. But what is the effect? So the effect is it is just rotated around the origin, and nothing else has been changed about this set. Now we can see that this inverse transformation of this rotation. So R of Z is onto and one-to-one function on the entire complex plane. So if this is onto and one-to-one, then we can talk about what is the inverse of this rotation transformation. Okay, so if W is equal to R of Z, and we know what is R of Z. So R of Z is basically R e raised to power iota theta multiplied by e raised to power iota alpha. Now what is the inverse? So this is basically Z. So we can calculate the value of Z in terms of W. So this becomes e raised to power minus iota alpha into W. Now if W is equal to, so if we write down this W in its polar form, rho e raised to power iota phi, then this inverse function becomes, so Z is equal to F inverse of W is equal to rho e raised to power iota phi minus alpha. Now as we can see that if we transform using this rotation transformation, then we are rotated by an angle alpha. And if we use the inverse transformation, then we can observe that we just subtract this angle alpha from the argument. So in other words, we are rotating in the opposite direction of alpha. So that's why we can easily observe geometrically as well that this is the inverse transformation of the rotation. So precisely we have the following description. So this is R inverse of W, which is equal to W e raised to power iota alpha. So at the end we have rho e raised to power iota phi minus alpha, and this is one-to-one and onto mapping on the entire complex plane. Now the next linear transformation that we want to discuss is magnification. Now for magnification, we take B to be equal to 0, and we take A is basically K, which is a real number. Okay, so K is a real number, and it is in fact a positive real number. So in this case, the transformation becomes, so M of Z is equal to, so KZ. So if Z is equal to X plus iota Y, then the transformation M becomes K into X plus iota K into Y. Now in this case, we have further two cases. So depends if K is greater than 1 or if K is less than 1. And of course, if K is equal to 1, then we can see that there will be no change. Okay, so if K is equal to 1, so this is just identity. Okay, so M of Z is equal to Z, and this transformation is not doing anything. It is just an identity transformation. So we have this transformation, which is Kx plus iota Ky, and of course it depends whether the value of K is less than 1 or the value of K is greater than 1. So if the value of K is less than 1, then it reduces the distance between the points by a factor K, and if K is greater than 1, then it has the effect of stretching the distance between the points of the factor K. So in this case, we can see that this is the case when K is greater than 1. And similarly, if K is less than 1, then it will be squeezed down. Okay, so this triangle will be squeezed down to a very tiny triangle. Okay, so this is the case when K is less than 1, and this is the case when K is greater than 1. Okay, so why this is happening? So when we have K greater than 1, then we can easily see that we are scaling up this X coordinate and Y coordinate by the same scale K. And if K is less than 1, then we are scaling down. In other words, we are kind of squeezing this triangle to a very tiny triangle if k is less than 1. Now, given a linear transformation, we can observe that L of z is equal to az plus b. Okay, so if we write down this a in the form L of z is equal to k e raised to power iota alpha z plus b, and of course we can do that because a is a complex number, and we can write down this complex number a in the form k e raised to power iota alpha. Now we have observed through 3 different cases. When we choose some particular cases for a and b, then we have translation, we have magnification, and we have rotation. And from this transformation, we can observe that this k is basically responsible for the magnification, and this alpha is responsible for the rotation. Okay, so this is for rotation, and this k is for magnification, and this b is responsible for translation. Okay, so we can say that if this is the linear transformation, then this linear transformation rotates the point through this angle, which is the argument of this complex number a, and it magnifies this complex number z by the factor k. And of course, if k is greater than 1, it will be scaled up, and if k is less than 1, it will be scaled down, but it is always a non-negative, in fact a positive real number. And of course, in this transformation, b is responsible for the translation. So we can say that a linear transformation is a composition of translation, rotation, and magnification. And given a linear transformation, L of z is equal to az plus b, we can calculate its inverse transformation because it is 1-to-1 and onto the w plane. So that's why we can calculate its inverse. So if w is equal to L of z, then we can calculate its inverse. So we can calculate the value of z in the following way. So az is equal to w minus b, and z is equal to w over a minus b over a. And this is in fact the inverse transformation, which is a function of w. And if we choose to write down z instead of w, then the inverse transformation becomes, so L inverse of z is equal to z over a minus b over a. And of course, we can see that if we compose L with L inverse of z, then we will get z. In either way, in other words, if we apply L first and then apply L inverse, then we again get z. So these are inverse transformations of each other. In other words, geometrically speaking, if I apply L, then I will be translating, rotating, and magnifying it. And if I apply the inverse transformation, then I will be reversing the whole geometrical process. So that's precisely is the inverse transformation of linear transformation. Now in this part, we discussed the geometrical meaning of linear transformations. In the next part, we will discuss some examples about these linear transformations.